In today's video, we're going to learn how to work with the reciprocal functions, the secant, cosecant, and cotangent. Now, the good news is that they work with sine, cosine, and tangent. So we already know those, and we're really comfortable with them. So we're going to introduce now the reciprocal ones. So our first one here, secant, is the reciprocal of cosine. So we say the secant of x is 1 over the cosine of x, where cosine of x is unequal to 0. We know that when we have a 0 in the denominator, it's undefined. And so that's why we say when cosine of x is unequal to 0. The secant is the reciprocal of cosine. The next one here is the cosecant. It is the reciprocal of the sine function. Again, where sine is unequal to 0, since sine is now in the denominator. And when we have a 0 in the denominator, it is undefined. And so the cosecant is the reciprocal of the sine function. Those are the two that students get confused the most because they want to put sine with secant because they're both s's, and they want to put cosine with cosecant because they're both c's, but that is not the case. Secant is the reciprocal of the cosine, and cosecant is the reciprocal of the sine. This one they don't confuse as much. So our cotangent here is the reciprocal of tangent. So that's the one that's a little bit more obvious for students. And again, we say when tangent is unequal to 0 because our tangent is in the denominator. Now we learned that tangent was sine of x over cosine of x. And since they are reciprocals, we can say that the cotangent of x is cosine over sine. So tangent was sine over cosine, cotangent is cosine over sine. We'll use that quite a bit later when we're verifying identities. It tells us the graphs of each of these reciprocal functions will include vertical asymptotes whenever the denominator is 0. So right here we just said if cosine is 0, that makes this undefined. And back in our rational unit, we learned that if 0 is in the denominator, it causes a vertical asymptote. So that's what that's telling us there. To find the exact value of the following expressions, we're going to use what we know already from the unit circle and our sine, cosine, and cotangent. And tangent. So in all of our use of the unit circle, we've said that the sine is the y value in the unit circle of an angle. And so if we talk about cosecant, which is its inverse, we say 1 over the y value is going to be our cosecant. So let's remember sine of pi over 3, that's going to be your easiest thing to do, is take the reciprocal one, so cosecant and sine are reciprocals, and find the sine value of pi over 3. Well, the sine value of pi over 3 is root 3 over 2. And so then we flip it for our reciprocal, because it is 1 over this. We keep the 1, change it to multiplication, and flip. So this would be 2 over root 3. As a reminder, we don't leave the square root in the bottom. We go ahead and rationalize, and so we multiply both the top and the bottom times the square root of 3. And so that gives me 2 square root of 3 on the top. On the bottom, that would be square root of 9, which is 3. All right, for our secant, that's the reciprocal of cosine. So this one is going to be 1 over x. So I would find the cosine value of 7 pi over 6. And so our cosine value of 7 pi over 6 is negative root 3 over 2. And so then we flip that. Negative 2 over root 3. We already said we go ahead and rationalize. And so this is going to be the same thing, but with a negative. All right, for cotangent, that was y over x was our tangent. And so this is going to be x over y. So tangent's y over x, cotangents are reciprocal, so that's going to be x over y. We go ahead and find the tangent value for 5 pi over 3. Again, you should be getting so good at these because we've done so much unit circle. And so at the 5 pi over 3, that is where our y value is root 3 over 2, and our x value is 1/2. And the y value is negative because that's in the 4th quadrant. So for this one, I don't even have to bother with this unless you already know that the 3 ones are the ones that end up as root 3. So keep that in mind. We'll go ahead and go straight to the cotangent one, though, and do the x over the y. yeah, the x over the y. So my x is what I'm going to keep in this case, and so that would be the 1/2. Then we change to multiplication and we flip our y, so that's going to be 2 over root 3. The 2's cancel out, and so we get -1 over root 3. And of course, we rationalize, and so that is negative root 3 over 3. All right. Now let's talk about the graphs of these. And so the graphs look a little bit different than what you're used to here. It's kind of a cool picture, though. So our first one, y equals secant, that we're going to talk about is the reciprocal of cosine. And so actually to graph these, the easiest way is to graph the cosine first. And so that's what we see right here is we graphed our cosine. So the first thing I would graph is y equals cosine x. With the cosine of x, our midline is at 0, so that would be this point right here. The amplitude is 1. So I'm going to go 1 above that and 1 below that, and that's going to be my minimum line and my maximum line right there. Cosine is the one that starts at the top, so there it is right there, and it's got a period of 2 pi. So at 2 pi, I'll be right back at that point. In between that, so 1 pi, I'm at the bottom, and then in between these, so at pi over 2, I am at the midline, and then at 3 pi over 2, I'm at the midline. So this is one full cycle of the cosine curve, and then it repeats, obviously. Well, we said when cosine of x is 0, that means when it's on the x-axis, it's going to create a vertical asymptote. So here's my first vertical asymptote at pi over 2, and then I've got another one at 3 pi over 2, and another one right here, and it keeps going for every single time that I touch the x-axis. So at all of these points, I will have a vertical asymptote. Now, we know that this is periodic, so it's going to go on forever. So when we write those vertical asymptotes, we write the first one, x equals pi over 2. That was this one right here. And then we say plus pi over, times k when k is an integer. And so that is because here's my pi over 2. And a distance of 1 pi over, then I have another one, and then a pi, and I've got another vertical asymptote, and another pi, and I've got another vertical asymptote. So this will define every single vertical asymptote that we have there. Now, the period for this graph is 2 pi, just like the cosine graph, because one period is one full cycle, and so that's one of the curves on top and one of the curves on the bottom. That's one period. So we have one period right here, and then we have another period right there, which is a distance of 2 pi. Anyway, so we drew our cosine graph, which is not part of the graph. That's why you see it as little dotted or dashed lines. Then we go to the vertex here when it's at a maximum, and we use that and the asymptotes to graph our secant graph. So at every max or min point, then that's going to be the vertex. You're going to graph towards the asymptotes because our asymptotes guide our end behavior. And there is the secant graph. Now, very quickly, I'm going to go ahead and show you how to put that in the calculator. That way, when you have your calculator and you want to graph, you can do that. There is no secant button on the calculator. So to do this, we set it up as a fraction. And so I did alpha y equals to get that fraction bar. And I do 1 over my cosine of x. Of course, we have it in radian mode because that's what we're always going to have in AP Pre-Cal. And then I hit graph, and so there is my graph. The window's a little bit different than the one that we have on the paper. You could always make it exactly the same window if you wanted to by going to window and then going to negative 4 pi and positive 4 pi. Now you'll see it exactly the same way as it is on your paper. So that's how you do the reciprocal trig functions in the calculator. You're going to go 1 over its reciprocal, which is cosine of x in this case. All right, so our next one here would be the cosecant. That is the reciprocal of the sine. And so if you were to put that in the calculator, that would be 1 over sine again. We're going to graph this one exactly the same way. You graph the sine function first. Again, it's not part of your graph, so it's going to have to be a dashed or dotted line. Anywhere it hits the 0 mark, we get a vertical asymptote because that's going to be undefined there. And at each of our max points or min points, then we get a vertex and we go down. This one has a period of 2 pi again. All right, for the ranges of these, it tells us right here that secant and cosecant are both from -infinity to 1 and 1 to infinity. And so this is the graph part, so it's coming from -infinity to that vertex point and then goes back down. So that's this one right here, -infinity to -1. Then it does jump up here to this top part, and so it would be from 1 to infinity. If we wanted to write the domain for this one here, we would say all real numbers except these vertical asymptotes. We're jumping over those points, so we would say pi over 2 plus pi k. And so that would give me every single number except for those vertical asymptotes that we are jumping over. All right, so let's look at our cotangent is the last one right here. If I were to put this in the calculator, I would put it in as 1 over the tangent of x. Just like the tangent had a period of 1 pi, this also has a period of 1 pi. So you keep that in mind. It is a little bit different when you look at this graph as a tangent graph. If you remember, the tangent graph started at the bottom and went in this direction. So they are in the opposite direction. Also, if you remember, the tangent of x had a vertical asymptote at -pi over 2, and then it had a other vertical asymptote at +pi over 2, where this one has one at 0 and one at pi. So the period is still 1 pi, but those vertical asymptotes are shifted. And if you remember why, with the tangent, the ones that became 1, 0, like this, that's where our vertical asymptotes were for tangent. When we flip it for the cotangent, that becomes 0 over 1. So we do get a number that does exist, 0 over 1. But then the ones that were 0 over 1 convert to this, making it undefined. All right, let's try and graph this so you can see how that kind of works. We'll start with our cosecant here. And so that is the reciprocal of the sine. And so what I'm going to do is I'm going to graph this as if it was sine first. And we should all be comfortable with graphing that because we did that already. Remember, this was the midline at 1. So at 1, I'm going to have a midline. 2 is my amplitude, so I'm going to go up 2 and down 2 from this middle line. And so that's where my sine curve would bounce back and forth with. We know the sine curve starts at the middle, so it would be right here. Now it does have a right pi over 2, so my first point is going to be right here. This was right pi over 2, or horizontal translation by pi over 2, so I moved it to the right. And so then from there, I have a period of 2 pi still. And so 2 pi would be right over here. Kind of off my graph a little bit. In between these two, I would have my middle point. And then this graph goes up and then down. And so right here, it repeats since it is a periodic function. All right, so now that we have these points, I could go ahead and sketch the picture for it, but I don't even need that. So I like just to draw those points right there. If you wanted to, you could do a dashed or dotted line to follow these points. But the reason why I drew it is because I know when it's on the middle line, that's when it's undefined. So I am going to get a vertical asymptote every time it's on that middle line. So I'll go ahead and draw all my vertical asymptotes here. Even put this one right off the paper here. All right, so now we've got our vertical asymptotes. Now we can go ahead and sketch our picture. So I go to my max or min point, and then I use my asymptotes to guide my end behavior, and I go ahead and sketch my picture for the cosecant. And so at every one of those max mins, I'm going to have a vertex point there. And so my graph looks like this. All right, so let's answer some of these questions down here. For the domain, again, that's all real numbers except for my vertical asymptotes. And so my first vertical asymptote is right here at pi over 2. So I'm going to start with that one. Technically, if you used any of the other ones, it is equivalent, but we usually start with that first positive one there. So pi over 2. And then I've got another one, a pi distance away. So I'm going to say plus pi k, where k is an integer. All right. And so since I just wrote that, I'll go ahead and write my vertical asymptotes. Vertical asymptotes are always x equals because it is a vertical line, and that is pi over 2 plus pi k. All right, for the range, in this case, it's coming from negative infinity up to that -1, and then it jumps up here to 3 and goes up to infinity. So I am going to say from negative infinity to -1, and then I'm starting at 3 and going up to infinity. All right, so that gives us our domain, our range, our vertical asymptote, and our graph for our cosecant one. The secant would be very similar, except we start with the cosine graph. All right, for our cotangent graph, very similar to the tangent graph, we are going to take this middle part right here, the easiest way I think it is, better said. We're going to take this part right here, the bx minus c, and we are going to set it equal to its original asymptote. And so the original asymptote on the cotangent is this 0 right here. And so I set that equal to 0, and now I'm ready to solve. When I divide by 2, I get x plus pi is equal to 0, because 0 divided by 2 is still 0, and I move that over, and I get one at negative pi. So my first asymptote is right here at negative pi. Now the regular period is 1 pi, so if there was no b value, my next one would be right here, and then the following one, and so on. But we have changed our period because we have a b value there. So just like with the tangent, I take pi and I divide it by the b value. So the period on this one is pi over 2. That's pretty small, so we're going to have a bunch of graphs here. So pi over 2, that's this one right here. And then pi over 2 is on the y-axis, and pi over 2 is right after that. So we are going to have a ton of these. I'm going to go ahead and sketch these. They are dashed lines. Remember, asymptotes are not part of the graph either. And so there is our graph. Now, we are going to go ahead and sketch the rest of the picture. And so we've told you guys before, as long as you have the asymptotes in the correct location, and then you have your middle point. The middle point has not moved up or down, so it's just going to be in the middle of this. And then, of course, you want to have it in the correct direction. And so cotangent starts from this side and then goes down. So we're going to start from here and go down. If you wanted to find this exact location, you can plug in points, but we are not grading you on that. We're only grading on the sketch. So the asymptotes need to be in the correct location, and that middle point and direction need to be correct. Since the period was so small on this, we've got a bunch of these that we can see on this particular graph. And so you have something that looks like that. All right, time to continue with the information now. So we'll start by writing our domain. Again, we are skipping over those vertical asymptotes, so we're going to have all real numbers except for the x values of our asymptotes. I would use 0 as the first one here since there's already an asymptote at 0. And then there's 1 every pi over 2, so I say pi over 2 times k, where k is an integer. And so then our vertical asymptote would be pi over 2 times k. All right, our range, this one's easy, negative infinity to infinity, since it's starting from the bottom and going up forever. All right, so let's talk about some of the questions that you'll see on these on the AP test, and our test for that matter. It says, let f of x equal 3 times the secant of 2x. Which of the following is a vertical asymptote on the graph of f? There's a couple different ways that you can approach this. You can look at this graphically, you can look at it several different ways. So we'll look at it a couple different ways. This one here, the first thing I would look at is the period of this is 2 pi divided by my b value of 2, so I know I have a period of pi. And so if I thought about the graph of this, this is the reciprocal of cosine. And since it has not moved left or right, then I know my top point would be right there. It would go and then come back. And so this would be a distance of 1 pi because we just found the period right here. So in the middle here would be pi over 2. And so then this would be pi over 4 and 3 pi over 4. So the reason why I just did that is because we said when it hits the x-axis is where my vertical asymptotes are. And so now I can see I have one right here at pi over 4. And so I know my vertical asymptote is this one right here. I can also rule both 0 out because that's at the top, pi over 2 is at the bottom, and pi is at the top again. So I know those aren't my vertical asymptotes. So that's one of the ways we can do it. All right, so let's look at this one here. This is the reciprocal of sine, since it is cosecant. And so again, the first thing I'm going to do is take that 2 pi and divide by that b value, which in this case is pi. And so the period here would be 2. All right, so we know that the sine graph looks like this. It's not moved left or right, according to this. And so that's all that I really need to know is if it's moved left or right, because then I know where the starting point is. So my starting point is right here. The period is 2, which means this is 2 right here. And then in between that, it would also be at the midline. And I only care about those midline ones because when it is 0 is when it gives me that vertical asymptote. And so I can see that at 0, it is at 0, at 1 it's at 0, and at 2 it's 0, so that is my vertical asymptote right there. All right, the next one here says 3 cosecant of theta over 2. Which of the following gives the range of h? All right, so our range, if you think about the way these are, so sine and cosine are the functions, that would be our midline, our lowest line, and our biggest line there. And so these are always going to come from this top one and from this bottom one. So we know it's going to be negative infinity to whatever the bottom line is, and then the top line to positive infinity. So I can think about this as the sine graph. And so I know the midline is when there's a vertical translation. Since there's none here, then I know this is 0. The amplitude for the sine, cosecant does not have an amplitude because it goes up forever, but sine has an amplitude of 3 here. So I would go up 3 from 0 and down 3 from 0, which gives me negative 3 and 3. So I know this is going to come from negative infinity to negative 3, and then positive 3 to infinity. So C is my answer. All right, let k of x equal the negative 5 of cotangent 2 pi x. Which of the following is a vertical asymptote on that graph? Remember we said just like the tangent one, you want to take this center part right here and set it equal to the original. So I'm going to take 2 pi x and I'm going to set it to the original, which in this case is 0, so it makes things a lot easier. I can divide by 2 pi here, and I get x is still 0 because 0 divided by 2 pi is still 0. Then I find my period. And so that is pi over 2 pi. And so the pi's cancel out and we get 1/2. And so every half after 0, I'm going to have a vertical asymptote. And so B is my answer for this one. All right, the last thing we're going to talk about is solving with these. We did quite a bit of solving with sine, cosine, and tangent, and so this is very similar. So let's look at that. Just like we did with the sine, cosine, and tangent, we have 4 cosecant x plus 3, and g of x is 11. What are the x coordinates of the points of intersection? And of course, you really want to look at that interval so that you know where you're getting your answers from. So I take 4 cosecant of x plus 3, and I set it equal to the 11. Now we're going to solve just like normal, so I subtract that 3. And then we divide by 2. I'm sorry, by 4, and we get 2. So this is the part that's a little bit different. So right here, we would look on the unit circle when we got to this. The different part, or the additional part that we have to do now, is cosecant of x is the reciprocal of sine. So I can actually change this to sine and flip that. And so now we're looking for where sine is 1/2 between 0 and 2 pi. And so sine is 1/2 at pi over 6 and 5 pi over 6. All right, the next one here, again, a point of intersection. So my first step is going to be to go ahead and set these equal to each other. And now I'm going to solve. So I'm going to subtract this 3. So I get negative 1/2 secant x is equal to 1. I multiply both sides times a negative 2. And so I get secant of x is equal to negative 2. And this is where we do the reciprocal. So secant, its reciprocal is cosine of x, and I flip this. So now we're looking for where the cosine of x is negative 1/2, and that is true at 2 pi over 3 and 4 pi over 3. And again, that's because it was between 0 and 2 pi. If it didn't have that interval 0 to 2 pi, then you have to write the general solutions like we did with the other trig functions. All right, our last one is going to be a calculator one, just so that you can see how do we plug that in the calculator. We already talked about how to solving with the calculator with the trig once. It's not any different than that. So right here, we've got let p of x equal 3 minus 1.7 cotangent of 0.5x minus 1. What are the coordinates of the points where p of x is equal to 2? So what we are trying to solve is this 2 equals 3 minus 1.7 cotangent of 0.5x minus 1. Now, you can't put this in the calculator because I told you we don't have a cotangent button in the calculator, but I can rewrite it as a tangent. So I do 3 minus 1.7, and then I do the tangent of 0.5x minus 1. So tangent and cotangent are the reciprocals of each other. So I can rewrite this as the reciprocal. So 1.7 times, I change that to tangent over, I'm sorry, tangent in the bottom with 0.5. So to put that in the calculator, I'm going to use my fraction key. I get, oh, I forgot the 3 actually. 3 minus, now I use my fraction key, 1.7 tangent All right, so I made it look exactly the way it does on my paper by hitting that alpha y equals and leaving that in the fraction form. It makes things a little bit easier on order of operations. Now we want to know when that is 2. So I can put a 2 into y2. And one of the things I showed you is they're giving me an interval of 0 to 2 pi. So that's really the only thing I care about is where the solution is between 0 and 2 pi. So I would come to my window and I do 0 and 2 pi so that it only shows me the interval that we care about for this question. And so here is its graph. I can see this has one solution now. Now these graphs are periodic, so there's a number of different solutions. By limiting it to that interval, then I found the only one I care about, which is that one. I hit second trace intersect, enter, 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 And there it is at 4.078. Remember, you want to leave at least 3 decimals on the AP test. So my x is equal to 4.078. Obviously, the calculator makes it a lot easier than just solving. All right, that's our video on reciprocal trig functions.